Hey everyone, and welcome to The Explainer. Okay, today we are tackling a truly massive, frankly fascinating topic. We're going to completely demystify the wild journey of taking a machine learning project from a mere fragile little idea all the way to a fully automated production-ready factory. So if you've ever found yourself wondering how top-tier tech teams actually build, scale, and maintain ML models out there in the real world, well, you are in exactly the right place. Let's get into it.
But hold on. Before we go anywhere, I want to challenge a pretty common assumption. We really need to ask, is machine learning actually the right solution for your problem? Look, ML is incredibly powerful, no doubt about it, but it's not magic. It is expensive, it's time-consuming, and it's highly complex. Actually, a lot of the time, a much simpler non-ML solution, like a basic rules-based engine, might honestly just be better and faster for your specific business needs. It is absolutely vital to confirm you actually need ML before you write a single line of code.
All right, assuming you do need it, here is our roadmap for navigating the machine learning lifecycle. We'll start with Phase 1, assembling the team. Then move into Phase 2, ideation and planning. After that, it's Phase 3, measuring success, Phase 4, the experimentation phase, Phase 5, building ML pipelines. And we'll wrap the whole thing up with Phase 6, production and ethics.
So let's jump right into Phase 1, assembling the team, or, building your ML squad.
Here's the thing. Building a production-ready ML system is definitely not a solo sport. It requires bringing together a highly specialized group with incredibly diverse skills. Now, keeping it real, in smaller startups or operations, you might have individuals wearing multiple hats, but the core responsibilities, those stay exactly the same. Everyone brings a unique focus and a specific deliverable to the table. You've got your ML product manager, who aligns the project with business goals to deliver the product requirements document. Then the data scientist focuses heavily on statistical analysis. The ML engineer, they're the ones building the actual deployed model, while the data engineer builds the necessary data pipelines. And finally, DevOps handles the serving infrastructure. Establishing these team practices, shared definitions, and just really thorough process documentation early on is literally a lifesaver. It prevents massive confusion and friction later when the pressure is really on.
Moving right along, let's hit Phase 2, ideation and planning. Think of this as drafting your blueprint.
This is the stage where we sit down to estimate real-world feasibility and, crucially, where we manage stakeholder expectations. Because listen, if you treat an ML project like a traditional software build, you're going to have a bad time. Traditional software is, generally speaking, relatively linear with predictable timelines. Machine learning, on the other hand, is completely non-linear. It's probabilistic, highly uncertain, and driven by trial and error. It honestly requires a fail-fast mindset. Teams have to time-box their work, tightly scope down requirements, and try multiple different approaches, fully knowing that a bunch of them will just lead to dead ends.
To really see this uncertainty in action, there's this mind-blowing Kaggle competition anecdote. So initially, 350 teams jumped in and quickly pushed a model's prediction quality from 35% up to 65%. Pretty impressive, right? But then, over the next 2 weeks, the number of teams swelled to 1,400. That is a massive, massive injection of brainpower and effort. And yet, the top prediction quality barely budged. It just crawled up to 68%. In ML, your output is rarely proportional to your input, and real breakthroughs are just incredibly hard to predict.
And because of all that inherent uncertainty, doing rigorous feasibility checks is non-negotiable. Seriously, a model might look like an absolute superstar in a research paper, but then just completely faceplant in the real world. You have to ask the hard questions. Do we actually have enough data? Are there regulatory blockers we're ignoring? Will the features we train on even be available at serving time? This is especially crucial right now with the boom in generative AI. Gen AI requires heavily curated data sets. We're talking sometimes thousands of high-quality examples just for fine-tuning to ensure factual accuracy and avoid what we call confabulations or, AI hallucinations. Plus, you always have to balance prediction quality against hard technical costs like latency, RAM, and queries per second.
Okay, Phase 3, measuring success. Model metrics versus business metrics.
This is a big one. We absolutely have to differentiate between how a model performs in a vacuum and its actual, real-world impact on the business. If these two sets of goals are misaligned, your project is basically doomed from the start. Model metrics, these are the things data scientists love to geek out over, like F1 score, AUC, and recall, are a completely different beast from business metrics. Business metrics are what the executives actually care about, like increasing revenue by 12% or reducing data center energy by 30%. So the absolute crucial takeaway here is this.
great model metrics do not guarantee improved business outcomes. You can have a technically brilliant, state-of-the-art model that completely fails to move the needle for the business.
Let's look at a perfect real-world example of that exact disconnect. Imagine you build a customer churn prediction model with a staggering 95% accuracy. Those are incredible model metrics, right? You'd be thrilled. But what if the model only detects that a customer is going to leave 7 days before they actually pull the plug? If your business historically needs 30 days to deploy an effective retention campaign, well, that 95% accurate model is functionally useless. This right here is exactly why you must do early user testing. You have to prove a direct causal connection between the model's accuracy and the actual business goal.
All right, let's step into phase 4, the experimentation phase. We're going inside the lab.
This is the highly iterative, almost messy core of machine learning. It's where your data scientists really tinker to find the right features and architecture. But this experimentation process requires immense discipline. First, you have to determine a baseline performance. That's your measuring stick. Then, you make single, very small changes. For example, maybe you just change the learning rate to 0.001. If you go in and change 5 things at once, you're never going to know which one actually caused the improvement. And finally, you record absolutely everything. Oh, and be warned, you have to constantly look out for hidden noise in your experiments. Seemingly harmless things, like data shuffling or variable initialization, can artificially skew your results, totally tricking you into thinking you found a breakthrough when you actually haven't.
I genuinely love this mindset shift. Experiments with poor prediction quality are still useful to track. They signal which approaches won't work. You really have to reframe failed experiments. Don't see them as project failures, but as essential, clearly mapped data points. Handle those wrong predictions gracefully. And here's a pro tip for you. While the lab is busy running all these experiments, your engineering team should concurrently start building out parts of the end-to-end pipeline. It saves a ton of time later.
Which brings us perfectly to Phase 5, building ML pipelines. Welcome to the automated factory.
We are now pivoting from that static, highly experimental lab environment to the dynamic, automated factory of ML pipelines. But to understand why we even need pipelines, you have to ask yourself, why do models go stale? Well, it's pretty simple. The real world changes. Let's say you build a model to recommend clothing. Well, consumer trends shift incredibly fast. A clothing model trained last month is probably already out of date today. Now, on the flip side, if you're building a model to identify flower species, flower characteristics stay stable, so that model has a much longer shelf life. But for any dynamic data, static models degrade surprisingly quickly. They need continuous retraining. And that continuous retraining, that is handled by an automated pipeline flow. Think of it like an assembly line. It starts with a data pipeline, which constantly generates fresh training and test data sets. That fresh data feeds right into the training pipeline, which trains a brand new model. Then, the validation pipeline steps in, acting kind of like a quality control gatekeeper, comparing the shiny new model to the one currently running in production. If the new one is actually better, the serving pipeline takes over to deliver those new predictions straight to the user. Running this continuous training and deployment cycle daily is pretty much a recognized industry best practice to ensure your model is always reacting to the freshest data possible.
Now, looking closer at that serving pipeline, it usually delivers predictions in one of 2 distinct flavors. Online predictions happen in real time. A user makes a request, it hits an RPC server, and the model calculates the answer right then and there, instantly. Offline predictions, however, are pre-computed in the background, safely cached in a database, and simply looked up when the user needs them. And don't forget, raw model outputs often go through a post-processing step before the user ever sees them. This is where you might filter out toxicity, remove annoying clickbait, or just reorder the results to create a much better user experience.
And that brings us to our final stop, Phase 6, production and ethics, scaling and maintenance.
So, this is the big moment where the model scales up to meet the intense demands of the real world, utilizing heavy-duty compute resources like TPUs or GPUs. But listen, you cannot just deploy a model and walk away to grab a coffee. You need a strict production monitoring checklist. You've got to constantly look for skews or drifts, meaning the data the model is seeing out in the wild no longer matches the data it was originally trained on. You monitor quota limits, track latency, watch for outages, and log training failures. Catching these issues proactively is just essential, which is exactly why automated deployment and canary rollouts, where you cautiously release the new model to just a tiny fraction of users first, are non-negotiable for keeping the system safe. But here is the tricky part about monitoring quality in production. You often don't have immediate ground truth. Let me explain.
If your model predicts the weather 6 weeks from now, you literally won't know if it was right for 6 whole weeks. That is where proxy metrics become your best friend. A proxy metric is a measurable value you can track right now. For example, in a spam filter, you might not instantly know if a specific email is definitively spam, but you can track how many emails users are manually dragging to their spam folder. If that number suddenly spikes, boom, your proxy metrics is alerting your engineers to a serious degradation in model quality.
And throughout this entire crazy life cycle, you must manage your stakeholders effectively. Because the ML timeline is so nonlinear and uncertain, like we talked about earlier, it naturally causes a lot of friction with stakeholders who are used to traditional, predictable software schedules. The way you smooth over that friction is by proactively communicating very clear deliverables at every single phase. We're talking solid design docs early on, totally transparent experimental results during the lab phase, and crystal clear documentation for your production-ready implementations. Keep everyone in the loop.
All right, we've covered the whole journey, from that fragile initial idea all the way to a humming, automated, productionized ML pipeline. But I want to leave you with one final, pretty provocative thought. As your automated models scale up to make thousands or even millions of daily predictions that genuinely impact real human lives, how will you ensure they remain ethical, unbiased, and actively verified? Because honestly, building the machine is only half the battle. Guiding it responsibly is the true challenge. I highly encourage you to utilize community resources, places like Kaggle, to continue your learning journey and really dig into these global considerations. Thanks so much for joining me on this explainer, and keep learning.